Welcome to lecture 15 of module 3 database management system. In the last session we have seen about the concept of B plus tree, why we are using a B plus tree. B plus tree is actually an implementation of dynamic multi-level index, and we have also seen how to insert search keys into a B plus tree. Okay, so today we are going to see how to eliminate or how to delete search key from a B plus tree, from a given B plus tree. So when we delete such certain key values or search key values from this B plus tree, we have to make certain rearrangement in the data values or rearrangement in the search key values available in the tree. So how the rearrangement happens? Okay, in what all way we can rearrange those search key values? That is what we are going to see today. Okay, so B plus tree deletion. So this is the concept. Anyway, I am not going to read the concept. I am directly going into the example. By looking at the example, we can see the concepts. Okay. Now, so P plus tree deletion. So this is a given tree. Okay. From the tree itself, it is clear that this is of order P. Order is 3. Okay. The order is 3. How can we identify that whether the order of the tree? From the tree pointers we can identify whether we are having 3 tree pointers, then we can say that the order is 3. Okay, clear? That means a node can have maximum 3 children. That is the order of a tree. Clear? Now minimum number of search keys that can have number of search keys, maximum number of search keys that can have in a node is actually p minus 1. Okay, ഇപ്പോൾ ഒരു നോഡിനകത്ത് നമുക്ക് എത്ര സെർച്ച് കീ വാല്യൂസ് ഉണ്ടാകാം? ഇറ്റ് ഈസ് 2. ഓക്കെ, ഇവിടെ ഒരെണ്ണം വയ്ക്കാം, ഇവിടെ ഒരെണ്ണം വയ്ക്കാം. ഓക്കെ, മാക്സിമം 2 സെർച്ച് കീസ് ക്യാൻ ബി പോസിബിൾ ഇൻ എ നോഡ്. ഓക്കെ, അതാണ് മാക്സിമം നമ്പർ ഓഫ് സെർച്ച് കീസ് ഈസ് p minus 1. ഓക്കെ, നെക്സ്റ്റ് മിനിമം നമ്പർ ഓഫ് സെർച്ച് കീസ് ദാറ്റ് ഈസ് പോസിബിൾ ടു ഇൻ്റഗ്രേറ്റ് ഇൻ എ നോഡ് ഈസ് ആക്ച്വലി 1. How we got the value? That is the ceiling function of p by 2 minus 1. അതാണ് അതിൻ്റെ കണക്ക്. ഓക്കെ, ദാറ്റ് ഈസ് മിനിമം നമ്പർ ഓഫ് സെർച്ച് കീസ് എന്ന് പറഞ്ഞാൽ എന്താണ്? ദ സീലിംഗ് ഫംഗ്ഷൻ ഓഫ് ദ ഓർഡർ ബൈ 2 minus 1. So here we take p is 3. So 3 by 2 is 1.5. The ceiling function of 1.2 is what? 2. So 2 minus 1 is 1. So minimum there must be a value, a search key value in a particular node. Maximum it can have 2. Okay, അപ്പോൾ മിനിമം എന്തായാലും ഒരു വാല്യൂ ഉണ്ടാവണം. മാക്സിമം 2 പാടുള്ളൂ. ട്രീ പോയിൻറ്റേഴ്സ് 3 വേണം. ഓക്കെ, സോ ദിസ് ഈസ് ദ കോൺസെപ്റ്റ്. ഓക്കെ, സോ ദിസ് ഈസ് ദ ഗിവൺ ട്രീ. From that we are going to delete certain values. Okay, so let us check whether this is a B plus tree ആണോ എന്നുള്ള ചെക്ക് ചെയ്യണ്ടേ. ഫസ്റ്റ് നോഡ് ഈസ് 7. So whatever node that is coming to the left child of this node must be less than or equal to 7. Less than or equal to 7 ആണോ നോക്കിക്കേ. Yes, 1 and 6 is less than 7. Okay, now whatever node that is coming to the coming as the right child of this node must be greater than 7. Is it so? Yes, 9 is greater than 7. Okay, now this one again check. Whatever node that is coming, child that is coming to the left of this node is actually lesser than or equal to this value. Okay, so lesser than or equal to, so 1 is lesser than or equal to 1. Okay, so right answer. So whatever values that is residing in this node must be ranging between 1 and 6. Okay, between 2 and 6. Clear? 2 and 6 ആണോ നോക്കി. അതെ, 5 and 6 are between 2 and 6. Clear? So whatever that is coming to the right child must be greater than 6 ആണല്ലോ. അതെ, here also it is correct. Okay, ലെഫ്റ്റിൽ it is lesser than or equal to 9, റൈറ്റിൽ it is greater than 9 ആണല്ലോ. So now we are going to delete each all values from the tree. Okay, so first of all I am going to delete 5. I'm going to delete 5 from this tree. Okay, so you look whether the tree 5 is present. 5 must be available, must be there in the left child of 7. Okay, here it comes, here also, here it will be available in the left. Okay, no, to the right of 1. Okay, right of 1 will give 5. Okay, here it is 5. Okay, അപ്പോൾ വേറെ ഇൻറ്റേർണൽ നോഡ്സിലൊന്നും 5 ഇല്ലല്ലോ. ജസ്റ്റ് ചെക്ക് വെദർ എനി ഇൻറ്റേർണൽ നോഡ് ഈസ് ഹാവിങ് 5. നോ, ഓൺലി ദിസ് ലീഫ് നോഡ് ഈസ് ഹാവിങ് 5. Okay, so we can simply eliminate this 5. Why? Because even if we are eliminating this 5, we are not changing the rule. What is the rule? The minimum number of key present in a node must be 1. Okay, even if we delete 5, there is 6. Okay, so minimum number of key is there available. Okay, 1 key is there. Clear? So we can simply delete 5 from here. No issue, no rearrangement. Okay, rearrangement on the manda. Okay, let us see. See, we have deleted 5 and we have placed 6 here. Okay, 6 നമ്മൾ ഇങ്ങോട്ട് മാറ്റി. Okay, ക്ലിയർ? എന്തുകൊണ്ട് 6 മാറ്റിയെന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നമ്മളൊരു ഓർഡറിൽ വേണം ഇത് പ്ലേസ് ചെയ്യാനായിട്ട്. വി ഹാവ് ടു പ്ലേസ് ദീസ് സെർച്ച് കീസ് ഇൻ എ പർട്ടിക്കുലർ ഓർഡർ. ഓക്കെ, ലെഫ്റ്റ് സൈഡിൽ നിന്ന് വേണം തുടങ്ങാൻ. ഓക്കെ, ദാറ്റ് ഈസ് വൈ വി ഹാവ് പ്ലേസ് ദിസ് വാല്യൂ ഇൻ ദ ലെഫ്റ്റ് സൈഡ്. ക്ലിയർ? Even if you are shifting here, there is no change in there is no need for any rearrangement. Why? Because look at here, 1. The child of left child of 1 must be less than or equal to 1. Okay, so this center, the center child must be what? Must be between 2, must be greater than 1 and less than or equal to 6. Is it correct? Yeah, it is greater than 2 and lesser than or equal to 6. Clear? The right child must be greater than 6. Yes, it is correct. So there is no rearrangement required. Okay, fine. Next I am going to delete 12. Okay, this is much more complicated than the previous concept. So this is the resultant tree after deleting 5. So from here I am going to delete 12. 12 delete here. Okay, so 12 is available here. You just check whether 12 is available in any of the leaf any of the internal node. illa, internal nodes ilonnu 12 illa. Only the 12 is available in what? In the leaf node. Okay, so what you do is, first process is you just eliminate this 12. Okay, first process is you just remove this 12. Clear? But 12 remove ചെയ്യുമ്പോൾ what is happening here? The leaf node is actually is empty. What is the condition for the B plus tree? The minimum number of search key must be 1. Okay, is it satisfying the condition? No, not at all. Okay, so such a leaf is actually said to be in underflow condition. Okay, such a tree, such a node is actually undergoing an underflow condition. Okay, it is in the state of underflow condition. ഇതിനെയാണ് നമ്മൾ അണ്ടർഫ്ലോ കണ്ടീഷൻ എന്ന് ചോദിക്കുന്നത്. അപ്പോൾ ഇത് ചോദിക്കും, ഈ ക്വസ്റ്റ്യൻസ് ചോദിക്കും, when will a node becomes in underflow condition? So when there is no minimum value in that particular node, such node is called underflow node. Okay, so this leaf is in underflow state. Okay, so if the leaf is in underflow state, what we have to do is we have to borrow the search key from its siblings. If the sibling is having sufficient number of search keys, more than sufficient number of search keys, then he can borrow one from the sibling. Okay, sibling എന്ന് നമുക്ക് കൊണ്ടുവരാൻ പറ്റും. Who is the sibling of this node? This is a sibling. Okay, ഇതല്ലേ സിബ്ലിംഗ് എന്ന് പറയുന്നത്. Okay, അതിൻ്റെ സിസ്റ്റർ അല്ലെങ്കിൽ അതിൻ്റെ ബ്രദർ, ഇതല്ലേ സിബ്ലിംഗ്. This is the sibling. So from sibling I can borrow one value. Why? Because the sibling is having more than minimum number of search key. What is the minimum number of search key available? Must be there 1. It is having greater than 1 search keys. So one search key can be brought here. Okay, one search key can be brought here. Okay, you take the highest value and bring it here. Highest value has to be brought here. Clear? Now one more thing you must remember, that this search key cannot be brought directly here. The search key has to be brought through the parent node. Parent വഴിയേ കൊടുക്കാൻ പറ്റുള്ളൂ. Okay, the siblings cannot exchange anything. The sibling can exchange values only with the permission of parent. Okay, he will transfer it to the parent and parent will give it to the next sibling. Okay, so that is happened here. In 9 it will give it to here. Okay, this 9 will come here. Okay, that is the next state. Okay, this is the resultant table. Clear? After this rearrangement, so this 9 came here, this 9 came here, 9 clear? So a rearrangement happened here. Okay, അപ്പോൾ ഇത് റീഅറേഞ്ച്മെൻറ്റ് ചെയ്തു എല്ലാം ഓക്കെ ആയി എന്ന് പറഞ്ഞ് അടുത്ത സ്റ്റെപ്പിലേക്ക് പോകരുത്. യു ഹാവ് ടു ചെക്ക് വെദർ ദിസ് ഈസ് ഫോളോയിങ് ദ ബി പ്ലസ് ട്രീ കണ്ടീഷൻ. വാട്ട് ഈസ് ദ ബി പ്ലസ് ട്രീ കണ്ടീഷൻ? The value here in this node, the search key value is 9. Okay, so its left child must have values lesser than or equal to 9. Is that condition satisfied? Yes, obviously. Okay, here 8 is less than 9. Okay, so here it is okay. What about this? The right child of this must have the values greater than 9. Okay, must have values greater than 9. Okay, greater than 9 ആയിരിക്കണം ഇവിടെ വരേണ്ടത്. Okay, but here it is 9. Clear? So this has to be rearranged. അപ്പോൾ എന്ത് ചെയ്യുമെന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ what we do is we will remove this 9 and make it as 8. ഇതിന് നമ്മൾ 9 എന്നുള്ള 8 ആകും. Okay, such arrangement can take place. So this will be replaced by 8 because we are making modification in the internal node. There is no much issue here. So we are making it as 8. Okay, അപ്പോൾ ഇവിടെ നമ്മൾ 8 ആക്കി കഴിഞ്ഞാൽ എന്താണ്? 8 ആക്കി കഴിഞ്ഞാൽ this condition is satisfied. Okay, this value have the left to this must have less than or equal to 8 and right to this must have greater than 8. So this condition is obeying the B plus tree condition, B plus tree rule. Okay, so this is the resultant tree after deleting 12. 12 delete ചെയ്ത് കഴിഞ്ഞാലുള്ള resultant tree ആണ് ഇത്. Okay, next value we are going to delete is 9. That is from here I am going to delete 9, right? So I will blankly first step is I will remove this 9 and just check what all rearrangement has to be made. Okay, so in the first step I have removed this 9. Okay, so when I remove this 9, what happened? This node, leaf node, has become blank. This is not having minimum number of key. Okay, such condition is called underflow condition. So this leaf node is actually went into underflow condition. Okay, so if a leaf node is if a node is going into an underflow condition, what the solution is that we need to share the search key value from its sibling. If the sibling is having more than minimum number of search key. Okay, if the sibling is having more than minimum number of search key, he can share the search key from the sibling to this node. Okay, but unfortunately the sibling is not having minimum number of search key. Okay, ഒരു search key മാത്രമേ ഉള്ളൂ, അപ്പോൾ ഇതിന് ഷെയർ ചെയ്യാൻ പറ്റില്ല. Okay, so what we do is we will merge these two leaf node. Only that is the option. Okay, only that is the option. Clear? So we will merge these two values. So before merging we need to make one more condition. Before merging we will do one process. Before merging we look at the parent node. If the parent node is having any value, that will be shifted to here. Okay, that will be shifted to here and then we merge it. Okay, so 8 is actually present here, that will be shifted here, then will we merge it. Okay, അപ്പോൾ അങ്ങനെ മെർജ് ചെയ്യുമ്പോഴത്തേക്ക് ഇത് കിട്ടും. ക്ലിയർ? അപ്പോൾ നിങ്ങൾ നോക്കുമ്പോഴത്തേക്ക് ഇവിടെ ഒരു 8 ഉള്ളൂ, 2 8 ഇല്ലായിരുന്നോ? ഓൺലി സെർച്ച് കീ വാല്യൂസ് ഒന്നല്ലേ വരാൻ പാടുള്ളൂ. ഓക്കെ, അപ്പോൾ since these copied value also the merged value is same, we will write only one time. The search key value we will write only once. ഇത് 2 8 ആയതുകൊണ്ട് നമ്മൾ ഒറ്റ പ്രാവശ്യമേ 8 എഴുതത്തുള്ളൂ. ഓക്കെ, Now look, this parent node is actually empty again. Okay, parent node empty ആയി because അവിടെ നമ്മൾ വാല്യൂ താഴോട്ട് എടുത്തല്ലോ, അപ്പോൾ parent node empty ആയി. Okay, so this parent node has gone to this underflow condition. Okay, so in order to handle underflow condition, what is the mechanism? We need to look at the sibling. If the sibling is able to share any search key value, he can do it. Otherwise we can merge. Okay, look at the sibling. Yes, sibling is having value to share. It is having more than one search key. Okay, more than minimum number of search key. Okay, so it can share one. Clear? So he cannot directly give any values to its sibling. He can transfer only through its parent. Okay, so you'll take the highest value and transfer it to the parent. Okay, parent like 6 കൊടുക്കും. ഓക്കെ, പാരൻ്റ് എന്ത് ചെയ്യുന്നു, ആ 6 അക്സെപ്റ്റ് ചെയ്തിട്ട് ഈ 7 ഉണ്ടല്ലോ, പാരൻറ്റിൻ്റെ കയ്യിരിക്കുന്ന 7 യു വിൽ ബി ഗിവിങ് ടു ദ റൈറ്റ് സിബ്ലിംഗ്. ഓക്കെ, so this will transfer 6 here and the parent will transfer his 7 to the right child. Okay, this node. Clear? In that manner we can handle this underflow condition. ഉണ്ടോ, 6 ഇവിടെ വന്നു, ഇപ്പോൾ 6 ഇവിടെ നിന്ന് 6 ഇങ്ങോട്ട് വന്നുണ്ടോ, 7 താഴോട്ട് വന്നുണ്ടോ, ഇവിടെ ഇരുന്ന 7 താഴോട്ട് വന്നുണ്ടോ, താഴോട്ട് വന്നു കണ്ടോ. ദിസ് ഈസ് എ വേ. ഓക്കെ, now you check whether this tree is satisfying the B+3 condition. That is our next task. Okay, 6. So whatever values to the left child to the 6 must be the values less than or equal to 6. അതെ, 1 ഉള്ളൂ അല്ലേ. 1 ലെഫ്റ്റോട്ടുള്ളത് less than or equal to 1. Yes, right. 1 in the right child must be greater than 1. Yes, correct. ഇനി ഇവിടെ 6 in the right must having greater than 6, values greater than 6. Yes, 7. Okay, left of 7 must have values less than or equal to 7. അല്ലേ, less than or equal to 7 അല്ലേ. Yes, less than or equal to 7. Yeah, right. Next, right 7 the right. Okay, right child of 7 must have values greater than 7, right? 8 അല്ലേ, 8 എന്ന് പറയുന്നത് it is greater than 7. So B+3 condition is also satisfied. So this tree is B+3 is balanced and this is right. Clear? So next, from this resultant tree, next I am going to delete 8. Okay, next I am going to delete 8. So where is this 8? 6. Okay, 8 must be to the right of 6. 8 must also be in the right of 7. Okay, so 8 is available here. Okay, so first task is I will blankly eliminate this 8. Okay, and then check each conditions one by one. Okay, അപ്പോൾ ആദ്യമേ 8 അങ്ങ് റിമൂവ് ചെയ്തു. ഇവിടെ ഇരുന്ന 8നെ നമ്മൾ റിമൂവ് ചെയ്തു. Okay, we have removed 8. When we removed 8, what happened? The leaf node has gone into underflow condition. Leaf node has gone into underflow condition. അപ്പോൾ സിബ്ലിംഗ് ഹാവ് ഓൺലി മിനിമം നമ്പർ ഓഫ് സെർച്ച് കീസ്. സിബ്ലിങ്ങിൽ എന്താണ്, ഓക്കെ, ലീഫ് നോഡ് അണ്ടർഫ്ലോ കണ്ടീഷൻ ആയി കഴിഞ്ഞു. ഓക്കെ, അപ്പോൾ അണ്ടർഫ്ലോ കണ്ടീഷൻ ഹാൻഡിൽ ചെയ്യാൻ വാട്ട് ഇസ് എ മെത്തേഡ്? വി വിൽ ലുക്ക് അറ്റ് ദ സിബ്ലിംഗ്, വെദർ സിബ്ലിംഗ് ഈസ് capable to share one of the search key. No, he is not capable to share. Why? Because he is having only minimum number of search key. Okay, sibling is having only minimum number of search key, so he cannot share any search key to this node. So only solution is to merge these two nodes. Okay, only solution is to merge these two nodes. Okay, so before merging, what has to be done? Whatever value that is available in the parent node must be transferred to this node. After that we will merge it. Okay, അതായത് ഈ 7 നമ്മൾ താഴെ കൊണ്ടുവരും. 7 നമ്മൾ അവിടെ നിന്ന് റീപ്ലേസ് ചെയ്ത് താഴെ കൊണ്ടെത്തിക്കും. ദെൻ ദിസ് നോഡ് വിൽ ബി പ്ലേസ്ഡ് ഓവർ ദിസ് വൺ. ഓക്കെ, ക്ലിയർ? ഇപ്പോൾ രണ്ടും 7 ആയതുകൊണ്ട് വി വിൽ റൈറ്റ് ഓൺലി എ സിംഗിൾ 7. ഓക്കെ, ഇവിടെ നമ്മൾ ഒരു നോഡിൽ സിംഗിൾ 7 എഴുതത്തുള്ളൂ. അത് മനസ്സിലായില്ലേ? വൈ? ബിക്കോസ് വി ഹാവ് ട്രാൻസ്ഫേർഡ് 7 ഹിയർ and while merging the 7 is coming. While merging we are actually including 7. So two search key with the same value cannot be written. 7 7 എന്ന് എഴുതാൻ പറ്റില്ല. So you will write only a single 7. ഓക്കെ, അപ്പോൾ ഇത് കഴിഞ്ഞിട്ടുള്ള അടുത്ത ട്രീ ആണിത്. അപ്പോൾ അവിടെ എന്താ സംഭവിക്കുന്നുണ്ടോ? പാരൻറ്റ് ഈസ് empty, parent has got empty, and the parent is having only a single child because we have merged these two nodes. Okay, single ആയിട്ട് മാറി. Clear? Again look at here. This has gone into an underflow condition. This has gone into underflow condition. Why? Because it is not having any minimum number of search key. So this has gone into underflow condition. So one of the solution to handling this underflow condition is to we will share search key values from the sibling in the search key value share ചെയ്യാൻ നോക്കും. Okay, സിബ്ലിങ്ങിന് കൊടുക്കാനുണ്ടോ? Sibling is having? No, sibling is not having any search key value. Okay, so sibling is having nothing to share with this one because it is not having minimum number of search key. Okay, clear? Sorry, it is having only minimum number of search key. Okay, അപ്പോൾ അത് കൊടുക്കാനില്ല. So nothing to share. So another option is to what? Another option is to merge these two nodes. Okay, രണ്ട് നോട്ട്സ് മെർജ് ചെയ്യുക എന്നുള്ളത് മാത്രമേ ഇതിനകത്ത് സൊല്യൂഷൻ ഉള്ളൂ. Okay, so before merging, what has to be done? Before merging, we have to do an operation. What? The parent, whatever value in the parent to be shifted down. Whatever value in the parent must be shifted down. After that, we can merge. Okay, അപ്പോൾ ഈ 6 ഈ താഴെ വരും. 6 will come down. Okay, after that we will merge. Clear? അപ്പോൾ കണ്ടോ, ഈ 6 താഴെ വന്നു. കണ്ടോ, ഈ സ്റ്റെപ്പിൽ ഈ 6 താഴെ വന്നു. Now we can merge. So look at here. So here we have merged these two nodes into a single node. Okay, അപ്പോൾ അവിടെ ഒരു വാല്യൂ 1ഉം അടുത്ത വാല്യൂ 6ഉം ആണ്. അപ്പോൾ മെർജ് ചെയ്യുമ്പോഴത്തേക്കും ഒരു വാല്യൂ 1ഉം മറ്റത് 6ഉം ആണ്. So 1 6 is the merged node. Okay, so the merged node will be having value 1 and 6. Clear? Then we again check whether this condition is true, whether this condition is satisfying b plus tree condition. Okay, 1 in the left side, 1 in the left child to this 1 is having values less than or equal to 1, right? That is correct. Then 1 in the right child which is having greater than or equal greater than 1 is greater than 1 ആണ്, correct. 6 ആണ് അല്ലേ? 6 in the right child which is having greater than values greater than 6. Yes, it is having values greater than 6. Just remove this one. Okay, it is having values greater than 6, right? So this is the final tree is actually the resultant tree. Okay, so this is supposed to be our resultant tree. Okay, final result. Okay, so this is how we will delete keys from a B plus tree. Okay, so we will check each node, and if any value is deleted, and if that particular node has gone into underflow condition, we have to make two necessary conditions. What is that? If the sibling is having enough value to share, we can share from the sibling. If the sibling is not having any value to share, we will merge those two nodes. Okay, before merging, what we will have to do, we have whatever value that is present in the parent has to be brought down. After that we will merge it. Okay, this is the operation. Clear? So this is the operation of what? B plus tree deletion. So we have studied both the B plus tree insertion as well as deletion. So these problems are very important. It will be surely asked in the university question, whether they will give a set of values and they will ask to perform deletion, or they will give certain values and they will ask to insert values into the B plus tree. Okay, so both these operations need to be studied very well. Clear? Okay, thank you.